Well, hello, everybody. Welcome to another stream with Joe, the crazy guy. We're going to be continuing on IPv6 here as we rattle on here. Oh, yeah. It's off to be fun, everybody. This is Nick Creeper. Enough of this. Alright, guys. Alright, how we doing today? It's your boy, it's Joe, coming at you. Just thought I'd have some fun real quick. Alright. Oh, I feel like crapola today, guys. I don't know what's going on. Really hope I'm not getting sick, because I'm getting scared if I'm getting sick. Really hope I ain't, guys. Really hope I ain't. But I feel like crap. I've been feeling like crap. Today's the worst of it. Well, it's just getting worse. Oh, so dizzy. But we shall strive on. We shall push on. So, all right. How's everybody today? Hope everybody's doing good. Yeah. Let's continue on. I know we got about halfway through that chapter 24 yesterday. We'll probably finish up this chapter today, and depending on how I feel, guys. Like I said, I'm feeling not feeling too good at all. Like I said, I haven't really been feeling good the last couple of days, but I've been trying to push myself through it. And it's really starting to really two things. I'm getting scared, obviously, with everything going on, with the pandemic going on. Did I catch it finally? I hope not. It's a freaking job that I've been working. I've probably been exposed to it countless times already. I'd be so mad if I got it, because I don't take too kindly to getting sick, let alone how this is going to affect me, if this is really what it is. I hope it isn't. Because the last thing I need to do is spread it to my family. All right. Enough of that. Let's 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 get right down to it, guys. Yeah. Let's finish up this chapter here. All right. So we're gonna jump right into we'll continue on with IPv6. We left off last night right before we started talking about IPv6 multicast addresses. And we're gonna we'll pick up right there where we left off. Get this up here. Chat. All right. I also got, we got Cisco Model and Lab up and stuff like that. I made some more updates to the Discord today, guys. I also added the invite to my about page on my Twitch channel too. So, at any time, if you don't catch the invite for it in chat, you can always go to my about page in my Discord channel, on my Discord channel, on my Twitch channel, and you can find the invite there too as well, guys. So you can just click on that thing that says Discord. How we doing, Tech Geek? How we doing today, my good friend? Man, I am a hurting mess today. But we're gonna get through. We're gonna get through this study today. We're gonna finish up chapter 24, talking about IPv6, multicast addresses. We had some good stuff. The other day, yesterday. Let me get up real quick too. So yesterday we did a pretty good lab. It's just the lab I did yesterday. Yeah. So we had a pretty decent lab yesterday. That we were able to successfully GitHub hates me, LOL. GitHub hates me too, LOL. GitHub is a pain in the butt. How's that? I was what was it? I didn't realize it, but I know, well, I realized what I did. I set up like I set up two-way authorization there on GitHub a little while ago, and I hadn't touched GitHub ever since I did that. And just recently, I've been trying to, just recently, I wanted to implement Git into what I've been doing with the stream here, and I didn't realize it once you set up two-way authentication. For some reason, when I try to upload a program, it uploads my content from a year ago. It's probably because it's trapped inside of some, and it's where it stages everything. That's why. But yeah, the Git, you have like that's something that we're actually gonna be going over Git and stuff like that here soon too. Once we get past a little bit more of the CCNA stuff, we're gonna be going over Git and how to properly use Git and stuff like that, because that's also part of the DevNet certification. So, yeah. So if you stay tuned and following the channel, we're gonna be diving into to more Git knowledge and how to properly use Git and stuff like that. But yeah, Git can be a definite pain in the butt. I'll tell you, it can definitely be a pain in the butt. It's funny because its principles should be easy to understand, but the implementation of it can get foggy, because dealing with the multiple branches, dealing with if something's staged and stuff like that. Sometimes it's hard to understand if something's in the staging prep, the staging prep area, whatever they call it. And then when you do like the when you pretty much load it to whatever repo you're loading it to, is is there something in that staging phase that's going to get loaded to whatever repo you're trying to add it to and whatnot. So yeah, Git can be a pain in the butt. And honestly, I've been using the HTML GitHub page to upload these two, because when I set up two-way authentication on my account, I didn't realize it, but I have to make tokens now to upload everything through Git on my command line, and I don't want to expose my token by accident live streaming, so people can just get into my GitHub account and do whatever they want. So I've been loading everything through the HTML GitHub page. But yeah, this is just this right here was the lab we did yesterday. So if you're familiar with like Cisco's networking devices and whatnot, this is just the actual running configuration for the routers that we were working on yesterday. So this was the lab right here. So we had R1, R2, R3, and what we did was we implemented. I was finally able to implement a working lab. I heard that doing that can cause issues. Is that true? What, setting up the two-way authentication, or just give me some more contents behind that. Either way, but obviously I just wanted to make sure my account was secure. That's the only reason why I did that. But I didn't realize that once you are uploading files to the HTML way, it probably it probably isn't the best way to be, like, if we were doing legitsies, you know what I'm saying, if we were working out on a, if we were working together as a team, and we were building something together, it probably wouldn't be best for us to be uploading it through the HTML GitHub page. You know what I'm saying? There could be some other issues with that. So I mean, that probably, even though it's easier, it is easy to just drop the file right down into it. There probably is some underlining stuff that could go wrong with doing stuff like that, especially if we're dealing with probably bigger projects and stuff like that. You probably don't want to be doing stuff like that. It is still best practice to be going through it through like the Git, this thinking Git bash here is always, it's still best practice, or using obviously the command line and stuff like that to upload your stuff to Git from there. But just to make things easier and not to expose my token, I just decided it was best if I just plug it, just drop it right in, right into my repo that I got here. So, what's neat though is because of the reason why I wanted to do this Tech Geek is, again, if you jump on the Discord, like, I made it so the reason why I did this was mainly for people who don't, per se, have like a GitHub account or anything like that, and they want to be able to look at the configuration files that I'm doing in Cisco Modeling Lab. So we can generate those lab configurations into a YAML file through CML. And then once I dump them on Git, I have it hooked to my Discord, and then if somebody doesn't need, you don't need to have a GitHub account or anything like that. They can just click on this link, and obviously it's just going to bring them to the GitHub page, but it's not going to ask them to log in or nothing like that. and then they can actually take a look at the running configuration files, as if this router was logged on and you had done the show running config command to take a look at that. And that's all this is right here. This would be the same thing as doing the show running config on that router. It's the exact same. It is all the information that you're gonna get. So you have all the interfaces. So the gig interface. Obviously, we didn't use IPv4 in this lab. It was all IPv6, and we used the EUI -64 command following the we did all I implemented all unique local addresses in that lab right there. And then what was a good learning thing is I was able to finally implement OSPF version 3, which is IPv6's version of OSPF between the other routers. And as you can tell, we have a couple of we created a couple different subnets in IPv6, and then we also implemented DHCP2. Take a look at that too right here. So we implemented DHCP version 6 here, which is IPv's 6 version of DHCP, and we're able to allocate addresses properly too as well, which is pretty neat. So yeah, so that was a pretty good lab yesterday. And again, so you can just run through. This would be router 2s here and whatnot. So pretty neat stuff. All right. All right. All right. Let's continue on here. All right. IPv6 uses multicast IPv6 addresses for several purposes, like IPv4. IPv6 includes a range of multicast addresses that can be used by multicast applications with many of the same fundamental concepts of IPv4 multicast. For instance, IONA defines the FF30::/12. All IPv addresses that begin with the FF3 as the range of addresses to be used for some type of multicast application. Additionally, different IPv6 RFCs reserve multicast addresses for specific purposes. For instance, OSPF version 3, FF02::5, and FF02::6, as the all OSPF routers and all designated routers multicast addresses respectively. So that's actually very similar to how OSPF version 2 on IPv4 works, where it was the multicast address, the 224.0.0.5 and the 224.0.0.6 address too, where it would use the .5 for broadcasting out those LSAs throughout the OSPF network, and then the .6 was mainly used by the designated router. All right, and there it is right there too. It's actually sitting right there, similar to how use of IPv4's address 224.0.0.5 and 224.0.0.6 for the equivalent purpose. Cool, that's neat. The next section focuses on IPv6 multicast address reserved for different protocols that first link. The first link local multicast address are multicast addresses used for communicating over a single link. The other type is a special overhead multicast address calculated for each host, called the solicited node multicast address. All right. Reserved multicast addresses. Stop for a moment and think about the type of control plane protocol discussed throughout this book so far. Some of the IPv4 control plane protocols used IPv4 broadcast to serve the message. Used IPv4 broadcast, meaning that the packet destination address was either 225.225.225.225. The address is for all hosts in the local area LAN, or a subnet broadcast address, the address for all hosts in a specific subnet. Those broadcast packets were then sent as an Ethernet broadcast frame destined to the Ethernet broadcast address of FFF. Okay. All right. While useful, the IPv4 approach of IPv4 broadcasts and local area networks, broadcasts required every host in a VLAN to process the broadcast frame, even if only one other device needed to think about the message. Also, each host had to process the frame, then packet, read the type of message, and so on before ignoring the task. For example, an IPv4 ARP request, an IPv4 in local area LAN broadcast requires a host to process the Ethernet IP, and ARP details of the message before deciding whether to reply or not. IPv6 instead uses layer 3 and layer 2 broadcasts instead of using layer 3 multicast addresses, which then in turn Ethernet frames into Ethernet multicast addresses. So let's read that one more time. IPv6 instead uses layer 3 and layer 2 broadcast instead of using layer 3 multicast addresses, which in turn causes the frame to use Ethernet multicast addresses. As a result, all hosts that should receive the message which is necessary for the protocol to work. However, hosts that do not need to process the message can make the choice which can make that choice with less processing as compared to IPv4. For instance, OSPF version 3 uses IPv4 IPv6 multicast addresses FF00:5, FF002:5, and FF02:6. In a subnet, the OSPF version 3 router will listen for the packets sent to those addresses. However, all the endpoint hosts do not use OSPF version 3 and should ignore those OSPF version 3 messages. Right? However, all endpoints hosts do not use OSPF version 3 and should ignore those OSPF version 3 messages. If a host receives a packet with FF02:5 as the destination IPv6 address, the host can ignore the packet because the host knows it does not care about the packet sent to that multicast address. That check takes much less time than the equivalent check with the IPv4 address. All right, list of all common IPv6 multicast addresses. All right, so what do we got? All nodes, FF02:1. All nodes, all interfaces that use IPv6 on a single link. All routers. OSPF designated routers. RIP, ERGRP, and then the DHCP relay. Very cool. All right. Space registry will show the IANA page that lists all the reserve values for the All right. In the example, it repeats the output of the show IPv6 interface command that shows the multicast address for used by R1 on gigabit 0-0. In this case, the highlighted lines show all nodes, addresses, all routers, and 2 for OSPF version 3 FF yada yada yada. We can take a look. Let's take a look at that. Let's actually start building a lab, guys. Six. B. One. Which is going to make a nice, we're going to create another IPv6 topology, guys. We're going to implement OSPF version 3 and DHCP version 6 on this lab too again, with a couple of hosts. We have a couple switch in every host just so I can demonstrate and show DHCP working properly, and then assigning dynamic addresses to the host in a proper fashion. So let's make, we'll make a couple links. And we'll get everything fired up, guys. And then once we get to the command line processing, I'll zoom in the scene too, guys, so you guys can see me work on the command line. We're just gonna fire up these 2 routers initially, just for now. All right, because they do take a couple minutes to get fired up. All right, but we're gonna we'll implement a similar scheme topology as we kind of did yesterday. Using the UEI, the EUI, oh, Gamer Golf, what up? a message. So Mickey Mouse gets a call from his lawyer. Lawyer says, "Sorry, Mickey, but you can't divorce Minnie because she acts funny." To which Mickey replies, "I never said she acts funny. I just said she's fucking goofy." What's up, Gamer Goof? How we doing? That was a good one. I like that. She's fucking goofy. That damn goofy, because he's so tall. That's awesome. You just pumped me up. You just pumped me up, Gamer Golf. All right. So, while these are firing up, we can continue on. Hold on 1 second. Kids have all lost their minds. Getting dumb on here. I remembered I hate snow. Just that a bit more than I hate IPv6. At least I could turn off. At least I could turn up. Wait, it's snowing where you're at, huh? Hey, you could. I have weather commands in the chat. Hey, you could check out my weather. My weather's actually not too bad today. What is the weather today? It's a whopping 36 degrees out. That's not bad. Wonder where you're at, where it's snowing right now. Either you're north than I. Because honestly, it's been the weather's been crazy, crazy nice lately for some weird reason. All right, so the command show IPv6 IPv6 interface command shows the multicast address used by router R1 on this gigabit interface. And that in this case, the highlighted lines show all the NOID addresses, FF2, all routers, yada yada yada, 2 OSPF version 3s, FF02::5 and FF02::6. Note that the IPv6 multicast addresses that the router interface is listening for and processing are listed under the heading join group addresses at the top of the highlighted section of the output. So I want to take a look at this today when we implement this new lab because I didn't take a look at this yesterday. So once we implement, we're going to implement OSPF version 3 like we did yesterday. We're going to take a look at that to see, because these two addresses, so the FF02::5 is the multicast address used by OSPF version 3. Obviously, just like how IPv4 was using the 224.0.0.5 address, and then the DRs, the designated routers, were using the 224.0.0.6 address. And IPv6, it's the FF02::6 multicast address that it's using on OSPF version 3 there. And then if we look here, we also have the DHCP relays, which is the FFF, the multicast address FFF.02::1:2. I don't know what that is. we're gonna be taking a look at that. How are you today, my good friends? It's snowing where you're at, huh? That crazy snow. Feeling like hot garbage today, Gamer Golf. Hot garbage. I hope I didn't catch this freaking shit, man. I really hope I didn't catch it. Because this stupid overnight cashier job, man. I've been exposed to it so many times with stupid stinking customers that refuse to wear stinking mask and everything else, and then come in coughing, sneezing all over the place, all over me. Like, again, I just hope I didn't catch this stupid stuff. Because I'm like the type of person that, like, I don't take too kindly to getting sick already. Like, I'm a hot mess when I get sick. Uh, in the last couple of days, I've been feeling worse and worse and worse. And today, like, well, it kind of started on Wednesday night where I was just getting dizzy. My head was spinning to the point where I wanted to like hurl all the time. And it was bad yesterday. I just kind of fought through it yesterday. Today, though, I can't shake it. Like this dizziness is just like insanity right now. Um, I'm like doing all I can right now just to maintain myself. That's why I don't think I'm gonna be able to stand up during the stream and do my usual whiteboarding if I had the opportunity to. I don't think I will be able to. I might freaking just fall over. All right. And what's weird is I get this. They kept on saying this weird taste in my mouth. Like I get this freaking weird taste in my mouth. Again, I'm scared. I'm gonna have to go get freaking tested now. All right. IPv6 RFC 4291 defines IPv6 addresses include the idea of IPv6 address scopes. Each scope defines a different set of rules about whether routers should or should not forward a packet and how far routers should forward the packets based on those scopes. For instance, you read earlier in this chat. You read early in this chapter about the link local addresses on the interface. A unicast IPv6 address, but with link local scope. The scope definition called link local dictates that packets sent to the link local unicast address should remain on the link and not be forwarded by any router. Most of the scope discussion of RFC 4291 applies to multicast addresses using the term multicast scope. Per the RFC, the fourth digit of the multicast address identifies the scope as noted in the table. So it's the fourth digit. So the fourth digit, obviously, it'd be this digit right here. All right. So interface, link local, site local, organization local, and global, no boundaries. Cool. It's done doing its thing. All right. All right. Let's get into it. All right. The first command. All right, let me get over my thingy scene. You guys can see this again. Let me. Right. Let me actually see how that looks. Hopefully that's clear. If that isn't clear, just tell me, guys. Gotta see how that looks. I need to move it just a tap. What's funny is you could see it coming through the back of my head now. All right. All right. That looks good now. You guys can see that pretty well now. All right, cool. All right, we'll continue on here. Yeah, that's pretty good. Okay. All right, so let's so we hit it with the first command. So we hit it with the first command. That is the when we're dealing with IPv6. So we're gonna hit it with the IPv6 unicast routing command. Okay. All right, that's the first command to initiate the router to enable the router to start using IPv6, because by default the routers are using IPv4 by default. Okay. So we're gonna do router OSPF version 3. All right, version 3, process ID 1, not I. Process ID 1. We're going to hit it with the router ID. All right, we're going to say 1.1.1.1. Okay. All right, that's just giving it the router ID for this router here. Okay. Then we're going to go into interface gig 0-0. All right, that's this interface between R1 and R2 here. All right, we're going to do we'll hit it with the IPv6 address. We'll do the similar yeah, we'll do a similar how we did it, how we've been doing it at least. So the FE00:1:1:1. All right, /64. Hit that with the no. Hit that with the no shut. All right, and then we're gonna say it's up. Then we're gonna say IPv6 OSPF process ID 1 area 0. And then let's do this. Let's move into interface gig 0-1 now. All right, we're gonna hit that with the IPv6 address. All right, we're gonna use the same address scheme, FF 1-1. That with the A now, :/64. Shut. All right, and then same thing, IPv6 OSPF process ID 1 area 0. All right, how's everybody doing out there in chat? Let me just get on. Let me make sure I'm monitoring YouTube chat today too, guys. Don't wanna. Sometimes I forget to monitor YouTube chat, so let me just make sure I jump on YouTube chat just in case anybody out there on YouTube. I just lost all my YouTubers. It's all good. All right. So we have that. All right. So we just set up OSPF and the other link. All right. So now let's exit. If I can spell exit right. Now we do IPv6 6 DHCP pool. Let's say net 1. That's fine. All right. Address prefix, and that's going to be the FB00:1:1:A:/64. All right. Exit. And then we can hit that finally with the do right. All right. I just caught a headline, and it turns out that the top in the world, only like 3 or 4 of them use Twitch. The rest all are on YouTube. That's pretty neat. Well, I stream on YouTube too. I stream on YouTube. While you're in R1, enable Telnet. No Telnet! We don't use Telnet around here. We use SSH. Well, by default, I mean, we could set it up. We could set it up if you want to see it. Because honestly, I can't even in Cisco Modern Lab. We could set up Telnet because in Cisco Modern Lab, SSH is actually broken. I mean, all we would have to do, yeah, we could set up Telnet. We could set up Telnet if you want to see that. It's already. Let me see. Yeah, by default. Hold on. We'll get to that. Don't you worry. We'll get to that. We shouldn't be using Telnet though. You know that. I actually just created. You know, it's funny that you said that too. We can do a packet capture, and I set up a new channel on the Discord too, where I was gonna start uploading packet captures to the Discord as well. So if anybody wanted to take a look at oh, did you really? Do you have Cisco Garrett Home Gamer Golf? That'd be pretty neat. Yeah, so you had to log into the VTY lines. Did you set it up with a password or without a password? And with a user, stuff like that. Because I mean, so you can obviously, so I mean, to talk about Telnet and SSH. So obviously, Telnet and SSH are a little bit different. SSH, you would have to set up like an SSH key pair and stuff like that. With Telnet, it's a little bit simpler, where you don't have to set up an SSH key, but you can still set up password parameters and stuff like that. The only problem with Telnet, obviously, and you guys probably know out there, is that Telnet, just a couple spare switches and a wireless AP, except I need to turn the wireless AP from lightweight to autonomous. Nice. Nice. We're going to be getting into, we're actually going to be getting into wireless and access points and all that, and autonomous units and stuff like that very, very shortly too. I believe that's actually the next chapter that's coming up, Gamer Golf. So that pumps me up that you just brought that up. But yeah. So again, to get back to the point of Telnet over SSH, and I can show you via a wire capture. Everything that passes through Telnet comes up as clear text, like you were just writing it out for somebody to see. I mean, obviously somebody would have to be sniffing on your sniffing on your wire and whatnot for them to see that. But if somebody was, they can just pick up that information right away. But yeah, that's pretty neat. So you had to do it on a couple switches. So you had to have some IPs, addresses on the switches and whatnot, right? All right, so for D, we'll give this the host name. We'll name this R2. All right, and let's IPv6 cast routing. All right, that's set up. So now we're gonna do router OSPF version 3, process ID 1, router ID 2.2.2.2, base gig 0-0, IPv6 address, FE 001 1 64 UIE shut, then IPv6 OSPF process ID area 0. And we just made our a successful adjacency via OSPF version 3. All right, so just like in IPv4 and implementing OSPF on an interface via IPv4, we just did that same exact. It's a similar command, just a little bit different, where you just have to enable IPv6 on the actual router. And then again, I haven't gotten so far to see. So in IPv4, you can go into the OSPF pretty much like there is a way to do the same thing with OSPF version 3. It's different. It's different to how it works on IPv4 than it does work on IPv6. Okay, but we just implemented OSPF version 3 on the interfaces again between R1 and R2, and then we just made our adjacency. Okay. All right. So that interface is done. So let's move over to gig 0-1 here. All right, and we're gonna again IPv6 address. We're gonna give this the FE 00:1:1: Bravo now /64 UIE. All right, we'll give that the no shut. All right, same thing, IPv6 OSPF. All right, OSPF process ID area 0. Okay, and then we'll exit. And then we're going to move into IPv6 DHCP. All right, pool. We're going to call it net2. All right, and then we're going to say address prefix. Again, this is similar to how it works over in IPv4. It's just different nuances to it all. Okay, it's just the nuances. And then we're going to say FE 00:1:1: Bravo /64. Okay, we can exit. We'll hit that with a do right now. Now let's fire these up. These I'm just firing up. I'm just firing up the unmanaged switches here. So these are unmanaged switches. Somebody argued, my buddy PGB Code, he also uses Cisco Model Lab as well. And I guess he didn't realize that these are unmanaged switches, but they're almost like hubs. Because if I were to set up, because they don't have an actual they don't have an actual management plane. There you go. They don't have an actual management plane, so I can't just go into the command line and do anything with them or set up VLANs or nothing like that. And what's crazy, what else is the reason why I was calling them hubs is because if I set up three interlocking into each other, they will create a broadcast storm. I did it before and I almost fried my computer one time just to see if it would happen, and it nearly happened. So pretty neat. But that's the reason why I was calling them hubs, because they're almost like they pretty much are broadcast domains, which is a hub. You know what I'm saying? Because it was broadcasting a loop indefinitely, and you could watch my CPU usage. It was going it went from like 10% all the way to 99 before I freaking unhooked it all. It went that fast. It was pretty amazing. Um, I'm not sure. Let me see if my Nightbot commands work in YouTube. If anybody on YouTube, this might work, it might not work. No, my Nightbot commands ain't working on YouTube. I'll have to fix that, guys. All right. Let's get over to this now. I'll zoom back in on the command line. We're over on PC1 now. I'll log into the PC1 to see if we got an IPv6 address. All right, and we did. All right, so we successfully got an IPv6 address here. All right. And here in a minute, we'll make sure we can ping everybody to All right, so we're good. We're cooking with gasoline. We got our IPv6 address for PCA PC2. All right, so the A is identifying that this right here. So this is in the A pretty much subnet. You know what I'm saying? That's all that. That's the reason why I put the A there, so we can identify it as what it is. Okay, so the same thing when we go over to B's little subnet. You'll see a same thing right here. So again, so there's the B subnet. Okay, that's the reason why I did that on purpose, so we can actually identify which actual subnet we're in. Okay, so we were able to get successful. So DHCP is working great. It's allocating dynamic IPv6 addresses. Again, here we go. So that's just identifying where we're at. So this is our prefix, obviously right here. So this is our prefix right here, guys. All right. So the FE00:1:1:B is our prefix. All right. And then the MAC address, the interface's MAC address is obviously 504. So no, it's actually 50. It's 0 and what? Remember we went over this yesterday with the conversions? You can actually look at that again. We'll look at that again. But the MAC address, oh, there it is. Yeah, 504:008 Foxtrot 52. Oh, so it's not doing that. Oh, that's cool. So it's actually not. Oh, okay. So it's not doing that on the actual host PCs. It's just pulling their actual MAC address. So there's the host actual MAC address right there, and you can see what this is doing. So it's pulling the MAC address. So the 5254. So 5. Oh, that's what it's doing. Okay. So yes, remember it's the 0. It's the second digit. So it's still doing it. Perfect. So it's still doing that because remember 0 to 2 invert. So there we go. So that's what it's. So again, it's doing the same logic with the EUI scope there. All right, and then it finishes off right there. Okay. All right. So that's cool. All right. So we're good. So hey, let's copy this address. Let's copy that. go over to PC. Let's go over to, so we're in PCA-1 there, and let's ping PCB-2. All right, and we're good. All right, so we have we have everything up and running. Again, that was we're getting faster at it now too, which is good. I like to see that. Getting faster at it. All right, so what was the show command? So that was the show IPv6 interface command. We'll say gig 0-1. And there we go. So there's that join groups right there. All right. There's our IP ad. So that's our global unicast address right there. There's our subnet. Our subnet is FE 00:1:1:1:alphas /64 EUI. It's represented right there. All right. Oh, I did FE, didn't I? I should have done FD. Wasn't thinking. It's okay. Let's do that. Yeah, because FE. Yeah, what was I thinking? And that's link local. That's our link local address right there. Huh, that's funny. It's funny that it worked too. But we're looking pretty good though. We're looking pretty good. All right. All right, so that's we've implemented this topology again pretty well, and we can do the show run too. All right, we can just take a look at the rest of the configuration here. All right, so again here's our IPv6 unicast routing, IPv6. All right, our IPv6 DHCP pool. There's our address prefix. Okay. All right. Again, we're not using any IPv4 in this topology. Okay. All right. So no IP address. It's going to state that still. Okay. All right. But here's our IPv6 address right there. All right. Our IPv OSPF area. All right. Same thing on our gig 01 interface. Okay. Same thing OSPF. All right. All right. Router ID. Router OSPF ID. Okay. All right. What we'll do. Show brief. Right. Want to move into the interface. say what are the IPv6 options? Filter connections based on access lists.
Bleeding really fast. He's using a paper towel. And it won't stop coming out. I'm gonna wash my hands.
Bloody noses over here. Bloody noses. Alright. What was I just doing? I don't remember. Before I get on a tangent with that, let's move on. Breaking this lab all over again. All right, so we took a look at that on the interface. So let's move back into the line. We'll do that same command. That's the do show IPv6 interface. So that's this right here is what we were just looking at, guys. So multicast address scopes. Move back over to the chat. Sweet tap dancing. My whole ISP router fell down, went boom for a bit there. Oh, hey baby, how are you? I don't know why that says my name when it says hugged. I gotta fix that. It should be saying you guys' name. When it says that instead of my name. But thank you for the virtual hug, baby. I appreciate that. All right. So, IPv6 RFC 4291 defines IPv6 addresses, includes the idea of IPv6 address scope. Each scope defines a different set of rules about whether routers should or should not forward a packet and how. Yeah, I'm tired. LOL. You bet you are, baby. And how to forward, and how far routers should forward the packet, based on those scopes. For instance, you read earlier in this chapter about the link local addresses on the interface, a unicast IPv6 address, but a link local scope. That the scope definition called link local dictates that the packet sent to a link local unicast address should remain on the link and not be forwarded by any router. Most scope definitions, most scope decisions in RFC 4291 applies to multicast addresses using the term multicast scope. Per the RFC, the fourth digit of that multicast address identifies the scope as noted. So the fourth digit. So one, interface local, packets remain within the device, useful for internal sending packets to services running on that same host. All right. Two, link local, host that creates the packet can send it out of the link, but no routers forward that packet. Five, configuration on routers intended to be more like link local. So routers forward must be less than organization local, generally meant to limit packets so they don't cross WAN links. Configuration. 8, configuration on routers tended to be broad, probably for an entire company or organization, must be the broader than the site local. Then we have the echo, which has no boundaries. Okay. All right. Breaking down the concept a little bit further. The packet sent to a multicast address with the link local scope should stay on the link local. That is the local subnet host. The local subnet hosts know that they can process a link local packet if they receive as the device, as do the routers. However, routers know to not route the packet to other subnets because of the scope. Packets with an organization local scope should be routed inside the organization, but not out to the internet over or over the link to another company. Note that the router can predict the boundaries of some scope like link local, but they do not configure to know the boundaries of other scopes, for instance, organization or local. All right. Comparing a few of the scopes in terms of where packets where the packets can flow. The higher the value in the fourth hex digit, the further away from the sending host the scope allows the packet to be forwarded. The table shows the progression top to bottom, while the figure shows in the example 3 scopes: link local, site local, organization local. In the figure, site local messages do not cross the WAN link, and organization local messages do not leave the organization over the internet. Okay, so it's just showing you the scope. We have link local, site local, and then obviously organizational local here. All right, if we were using the FE0E, obviously that would be global, that'd be internet. Okay, that would be processed out to the internet. All right, the FF0E, I apologize. All right, finally, the term link local has a couple of common uses. In IPv6 and can be configured as a result. The following description should clarify the different uses of the term. Link local addresses, an IPv6 address that begins with FE 80. All right, these serve as unicast addresses for a interface to which devices apply a link local scope. Devices often create their own link local addresses using the EUI 64 rule. A more complete term of the comparison would be like the link local, the link local unicast address, link local multicast address, an IPv6 address that begins with the FF02 that serves as a reserved multicast address to which devices apply a link local scope. Link local scope, a reference to the scope itself rather than the address. The scope defines the router should not forward the packets sent out in the address. Okay. Solicited Node Multicast Address. IPv6 Discovery Protocol, NDP. So neighboring discovery protocol, that is IPv6 version of ARP. Okay. All right. IPv6 calls it Neighbor Discovery Protocol. Okay. Replaces IPv4's ARP as discussed in Chapter 5. NDP improves the MAC discovery process by sending IPv6 multicast packets that can be processed by the correct host but disregarded with less processing by the rest of the host in the subnet. The processes use the solicited node multicast address associated with the unicast IPv6 address. All right, the figure shows to determine the solicited node multicast address associated with the unicast address stated with the predefined 140 bit prefix, so the 26 hex digit, okay, shown in the figure. In other words, all solicited node multicast addresses begin with the abbreviated FF02::1:FF. All right, and the last 24 bits of the 6 head digits, I copy the last 6 head digits of the unicast address in the solicited node address. Okay. All right. So this is just a big, huge. This is covering a wide array of addresses here, guys. Okay. All right. Note that the host or router calculates a matching solicited node multicast address for every unicast address on an interface. The example shows an example in which the router's interface has a unicast address of 2001:Delta Bravo 8:11111:1:1/64, and the link local address is Foxtrot Echo 80::Alpha Alpha. All right. As a result, the interface has 2 solicited node multicast addresses shown at the end of the output. All right. So again, we took a look at that. If we look at that again, over here in Cisco Modeling Lab, the link local address again begins with the FE80. All right, the FE80. All right, link local. Okay, link local. Obviously our address is different than their address. I used the FE. I should have used the FD. The FD is unique local. All right, so I should have went with the FD, but kind of feeling under the weather today, so I kind of like forgot. So I used the FE. That really doesn't matter. It's still routable. All right. All right. It's still a valid address nonetheless. All right. It's still a valid IPv6 address nonetheless. How's that? Nope. In this case, I want to go over unicast. Unicast address ends with the 00:0001, unabbreviated, resulting in an unabbreviated cisletter multicast address of Foxtrot 02 colon yada 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 colon 001 colon Foxtrot 00 colon 000001, whatever. This value begins with 64 with the 26 hex digit prefix shown in the figure, followed by the 00 colon 0001. The solicited node multicast address man, to the link of the, I'm stumbling over words now. To the link local address, Foxtrot Echo 80 colon alpha alpha colon alpha 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 ends in the alpha alpha colon alpha alpha alpha, as shown in the last line of the example. Okay, so again, here we go right there, and then we can take another look at that. So ours is obviously going to be a little bit different, and just you're laughing at me. My baby's laughing at me. Baby, drink some coffee. No, I can't drink any coffee. My head is already spinning. Death wish coffee. LOL. If I drink coffee right now, I probably will go under. So again, so all that's showing is so here's the last so here's our IPv6 address, the Foxtrot Echo 0 Delta colon Charlie 399er. All right, and then here is that address. So it's just pulling that address. Okay, here it is right there. So it's just let's just take another look at that. So it's using the 26 digits. So the 26th. Okay, so right here. So the 0. So it starts at the 0 Delta colon Charlie 399er. So again, right here. So the 0 Delta colon Charlie 399er of our address. Okay. That is what it's using as our solicited node multicast address. Okay. All right. So if we can understand that, all the way down to this 26 digit. Okay. 26 hex digit. Okay, so 1 2, where's our complete address? So 1 2 3 4. All right, remember 8 12 16 all the way down. Yeah, because when we get to that digit, yeah. So 8 4 times 6 equals 24. Yeah, so 24. So 24 ends right here, and then yeah, 24. Then we got into the 7th one. Which one are we looking at? It's the 26th hex digit. Yep, it's the 26th. So we have the 24th that ends right here, and then 25, 26. So right here, guys, at the so this right here would be where our you guys can't see that. What the light is. Oh, I was really lucky that didn't mess everything up. All right. So what I'm saying is let me delete that. bigger box, pick a different color. Make sure that's as small as it can get. So it's starting right here. This is where our 26th digit is, guys. Okay, so that's why you're seeing it again being repeated on this address line right here with the foxtrot 02:::1 foxtrot. Okay, so it's pulling it's where our 26th digit is for our solicitor-doing multicast address. Okay, all right, so it's using that same abbreviation. Okay, the foxtrot 02:::1 foxtrot. Okay, same thing again. Foxtrot 02:::1 foxtrot, and then obviously then it's implementing from the 26th digit of our IPv6 address into that address. Okay, giving us, that's what creates our our solicited Noid multicast address, guys. Okay. All right, so we understand that process right there. Very good. Note that in this case, our ones global unicast, yada 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 yada. Okay, so we understand that process now, guys. Still a little confusing, but I mean, it does seem like a lot, but in a sense, IPv6 is a little bit simpler once we get over some of the hurdles of. We just have to kind of put IPv4 on the back burner, and then once we do that, that's going to take us some of us a lot of time to do that. Especially myself, IPv6 actually, in a sense, is a little bit easier to understand. It's just less things to figure out, even though it looks more complicated. The unknown, unspecified IPv6 address, the : are all zeros. It's always all zeros. When you see the : it's all zeros. There's nothing hidden there. There's no hidden numbers, nothing like that. It's just all zeros. Okay. The loopback IPv6 address : 1 or 127 binary zeros with a single 1. All right. A host can use the unknown address : when its own IPv6 address is not yet known, or when the host wonders if its own IPv6 address might have problems. For example, host use the unknown address during the early stages of dynamic discovery, dynamically discovering their IPv6 addresses. When a host does not yet know what IPv6 address to use, it can use the : address as the source IPv6 address. The IPv6 loopback address gives an IPv6 host a way to test its own protocol stack, just like IPv4 with the 127.0.0.1 loopback address. The packets sent to : 1 do not leave the host, but are intended simply to deliver down the stack to IPv6 and back up the stack to the application of the local host. Okay. All right. Anycast addresses. All right. Imagine. All right. I am zoomed in again. Bloop. All right. Imagine that a router collectively needs to implement some services. Rather than have one router supply that service works best when implemented over several routers. But the host that uses the services need to contact only the nearest such service. The network wants to hide all these details from the host. Host can send just one packet to an IPv6 address, and the router will forward the packet to the nearest router that supports that service by virtue of supporting the destination IPv6 address. IPv6 anycast addresses provide that exact function. That any part of that name refers to the fact that any instance of the service can be used. All right. The figure shows the big concept with two major steps. All right. Step 1: two routers configure the exact same IPv6 address destined for an anycast address to some supported device. Okay. In the future, when any router receives a packet from that anycast address, the other router simply route to packet to the nearest router that supports that address. Okay. Step 1, identical addresses configured on both routers. So this is like, so I want to say, yeah, IPv6 interfaces can have multiple addresses, multiple IPv6 addresses on them, where IPv4 can only hold a secondary address on an interface, but IPv6 interfaces can hold multiple addresses. And this is like, for instance, of like having 2 servers across the country in different regions, in different areas, having the same IP address, and depending on which server is closer to the host at that particular moment, then that server obviously would get that packet depending on where it is in the region. But you can have 2 servers or multiple servers have the same exact IPv6 address there, and that's just what this is getting at, almost, sort of, kind of, yeah. All right, to make this Anycast process work, the routers implement the Anycast address must be configured. To make the Anycast process work, the routers implement the Anycast address. The routers implementing the Anycast address must be configured, and then the addresses, and then advertise a route for the Anycast address. The addresses do not come from a special reserved range of addresses. Instead, they are from the unicast address range. Often the address is configured with the 128 prefix, so that the routers advertise a host route for that Anycast address. At that point, the routing protocol advertises the route just like any IPv6 route. The other routers can tell the difference. All right, so the example shows a sample configuration on the routers. Note that the actual 2001 : whatever looks like a unicast address. The values can be chosen like any other IPv6 unicast address. However, note the difference. Anycast keyword on the IPv6 address command, telling the local routers that the address has a special purpose as in Anycast address. Finally, note that the show IPv6 interface command does identify the address as a Anycast address, but the show IPv6 brief command does not. So here we go. So there's that Anycast command right there, guys. The Anycast command. Okay. All right, and it's stating again with the any. Okay. All right, giving it the 128-bit, 128 prefix. Okay, right there. All right. So interface. So again, this interface is actually supporting two IP addresses, like I talked about earlier. So you can on IPv6, you can have multiple addresses on a single interface. Okay, where on IPv4 you can only hold a primary and a secondary IPv4 address on an interface. Okay. All right. Especially the subnet router Anycast address is one special Anycast address in each subnet. It is reserved used by routers as a way to send packets to any route on the subnet. That address value in each subnet is the same number as the subnet ID. That is, the address has the prefix value as the same as the other addresses, all in binary zeros in the interface. All right. IPv6 address and configuration summary. This chapter completes the discussion on various IPv6 address types while showing how to enable IPv6 on a interface. Many implementations will use the IPv6 address command on each router local area interface, and either the same command or the IPv6 enable command on a WAN interface. For exam prep, the table summarizes various commands and automatically generated IPv6 addresses in one place for review and study. So we have the IPv6 address, the the EUI/64, the unique local. So we have global unicast, unique local. Remember, global unicast, private, unique local. And that's what I'm saying. I should use the FD 00::8 on that one, but I biffed it. All right. The link local. All right. The all host multicast. All right. All routers multicast, various routers, protocols, and solicited node. Okay. So there's a chapter in review right there. All right. Some key topics. So conceptual drawing about the end-to-end dual stack for foreseeable future. All right. Rules for creating IPv6 and addresses in EUI rules. All right. IPv6 EUI -64 address formats. Conceptual drawing of how to create IPv6 addresses using the IUE rule. All right. Example of performing the bit conversion while using the IUE -64 rule. And that bit conversion, again, this was what I was talking about earlier. So here's that bit conversion that I was talking about. All right, 0 to 2 and 2 to 0, 4 to 6, 6 to 4, A to A, A to 8, Charlie to Echo, 3 to 1 and 1 to 3, 7 to 5, 5 to 7, B to 9, 9 to B, Foxtrot to Delta, Delta to Foxtrot. So there's that conversion rule right there, guys, and that's what I was talking about earlier. All right, some key terms we should know. Anycast, dual stack, EUIE, EUI, local address, link local address, link local scope, link local multicast address, site local, scope, organization local, scope, interface local, IPv6 address scope, solicited node multicast address, all node multicast, all routers, multicast address, routers, anycast. All right. And then it just goes over some more commands. All right. So, like I kind of hinted at the beginning, guys, I'm kind of under the weather today. Kind of under the weather today. I'm not feeling too hot. Well, I'm feeling really hot because I think I've got a temperature. But let me let's do this real quick. Let's fetch these configs off of these two devices, and we're gonna upload these up on. We'll upload these to GitHub. All right. That way, you guys can if you guys are more than welcome to join. Join the Discord server here, and then again, you can always find these labs over here, guys. Okay. And then I gotta figure out why my Nightbot commands are not working over at YouTube. Oh. I probably got my Steve Lab commands to work over there, but let's download the lab. Let's go to Git. File, upload a file. Drop that in there. All right. What's today's date? Today, well, it would give you today's date. IPv6 routing. Routing. IPv6 routing example. Okay. All right, so I just blasted that up on there, and as you can tell, it just populated here on the Discord, guys. All right. So that's it for now, guys. Like I said, I really am feeling under the weather today, and I feel awfully that I have to cut it short, but I need to try to get some more rest, and I hope you guys understand that. Let's go. I guess let's go raid. I don't know who's on right now. Let's go raid somebody that doesn't have that many views right now. I know I raided Bruce the other day, but he didn't even shout me out the other day. So, let's go raid. Let's go raid my boy, the Reaper of the Bacon. He's a cool guy. Let's go say hello to my boy, Reaper of Bacon. He's pretty neat. Alright, guys. You guys have a great night, and I will talk to you guys again here pretty soon. Alright, guys? Alright, guys.